Hi everyone. Today we're going to be talking about complex probabilities. Complex probabilities are sometimes called compound probabilities. And they're compound probabilities oftentimes because we're looking at multiple events occurring. And when we've talked about probabilities in the past, we've talked about things like rolling dice or spinning a spinner or flipping a coin and seeing what we land on. These are often pretty easy things for us to relate to and to know how they work. They're also things that we could experiment with and try out and see if our experimental probability matches up with our theoretical probability. Well, we're going to use a couple other examples today, like picking a card out of a deck of cards or pulling a marble or something out of a bag. The first thing that we need to understand when we talk about complex or compound probabilities of multiple events is we need to understand the idea of independent events and dependent events. When we say independent events, we're talking about events whose probability is not affected by previous events that have occurred. When we talk about dependent events, we're talking about events where the probability does depend on what's happened before. Let's go ahead and use some of our examples and see if we can categorize what we're going to do as independent or dependent events. I've got our definitions down there to remind us what they are. Let's start with flipping a coin. Let's pretend for a moment that I have a quarter and I flip a quarter and I got a heads on my quarter. If I flip that quarter a second time, am I more likely to get heads again or to get tails? Or am I equally as likely to get heads or tails? If I'm more likely to get a specific outcome, well, that means it's dependent. And if I'm equally as likely to get a specific outcome, that means that it's an independent event. Even though it may seem like flipping a quarter, if I get heads the first time, the next time I have to get tails, we all know that that's not true. Flipping a coin would be an example of independent events. It's possible for me to flip a quarter and land on heads, and flip a quarter again, and land on heads again, and flip on a quarter and land on heads again and again and again. It's possible, even though that's not very likely. But every time I flip a quarter, it's an independent event. The event is not dependent on what happened before. Let's take a look at another example. This time, let's roll a dice. And let's think about what would happen. Let's pretend for a moment that I roll a dice and I landed on a 6. Well, now, am I more likely to land on a 6 if I rolled that dice again? Or am I equally likely to land on 6 if I roll that dice again? Well, again, this is an example of an independent event. It doesn't matter what I got before when I rolled that dice. Every time I roll my dice, I am equally as likely to land on a specific number. This time, we're going to use the example of pulling a card from a deck of cards. In this case, I've pulled out the 6 of hearts. If I were to pull another card out from the deck, am I more or less likely to pick a 6 of hearts? Or am I equally as likely to pick a 6 of hearts? Well, this example is a little bit tricky because we might need a little bit more information to determine the answer to this. If I were to pick the 6 of hearts and take that 6 of hearts and leave it out of the deck, well, now I would be less likely to pick a 6 of hearts again. However, if I put that 6 of hearts back in the deck, I would be equally as likely to pick a 6 of hearts again. So this would be an example of something that can be both independent and dependent. Let's move on to another example. In this case, we're going to look at pulling out a marble out of a bag, and we're going to pretend like we can't see when we pull them out. So let's pretend we've pulled out a black marble from the bag, and we're going to make a second pick. We're going to ask really similar questions to what we've asked. Am I now more or less likely to make a specific pick In this case, maybe make the pick of another black marble? Or am I equally as likely? Well, this is another example of an event that can be both independent and dependent. It depends on if I put the marble back in the bag before I make my second pick. If I put my marble back in the bag before I make my second pick, it's an independent event. Each time it is equally as likely that the events occur. However, if when I make my second pick, I've kept my first marble out of the bag, well, my new probability is dependent on what happens before it. Our final example that we're going to do, we're going to look at spinning a spinner. Let's pretend that I've spun the spinner and I've landed on red, and I want to know if I spin that spinner a second time, what's my probability of landing on red again? Again, am I more likely to land on that certain color, on red in this case, or am I equally likely to land on that certain color, red? Well, each time that I spin that spinner, it's an independent event. It is not determined based on what happened before it. Understanding independent and dependent events when we're talking about probability is really important, and it will help us a lot with understanding how to work with compound and complex probabilities. Let's go ahead and move on to calculating our compound complex probabilities. Let's first remind ourselves what probability is. Probability is our desired outcomes divided by the total possible outcomes. Let's use flipping a coin as an example. I like to use this one because it's nice and simple, and our math is pretty simple to do. Let's think about the probability of flipping a coin and landing on heads. Well, my desired outcome would be 1, and my total possible outcomes would be 2. Remember that our total possible outcomes includes our desired outcome as well. That means I would have a 50% chance of landing on heads when I flip my coin. That's just a single or simple probability. Let's work now on a compound or a complex probability. In this case, we want to see how likely is it that maybe when I flip 2 coins, that my first coin lands on heads and my second coin also lands on heads. Well, we're going to determine this by figuring out the desired outcome over the total possible outcomes of my first event. In this case, 1 over 2. And we then want to find the desired outcomes over the total possible outcomes of the second event. Because this event is independent, it would also be 1 over 2. Once we've figured out those two probabilities, we're going to simply multiply them together to find the probability of landing on heads and heads. In this case, that would give us a 1/4 or 25% probability of landing on heads or heads. And hopefully it makes sense that the probability of flipping 2 coins and landing on heads and heads is less than the probability of flipping 1 coin and landing on just heads. We have more possible events that could happen when we flip 2 coins. And so it's less likely that we're going to land on heads and heads. Let's look at one final example. This time, we're going to pretend we have 3 coins. And I want to know the probability of landing on heads with my first coin, heads with my second coin, and tails with my third coin. Well, again, I'd want to find the desired outcomes over the total possible outcomes for each of those 3 events. In this case, it should be 1/2 for each of those events. All of these events are independent of each other. Once I've done that, I can multiply them together, and I can find the probability of that one event, heads, heads, and tails, happening. In this case, it would be a 1/8 probability or a 12.5% chance that that were to happen. Again, we see a decrease in our probability as our problems get more complex and as we add more elements to all of this. Let's use another example. Let's think about rolling a dice. And if I roll a single die, I want to know the probability of landing on a 3. Well, again, I'm going to write the desired outcomes over the total possible outcomes. In this case, one number is a 3, and there are 6 total possible outcomes. So 1/6 That would give me about a 16 and 2/3% chance of landing on a 3 when I roll a dice. Let's look at another example. This is the example of the probability of rolling 3 or an even number. Now it's important to note that this is not a compound event, because I want to know what is the probability of landing on a 3 or an even number, not a 3 and an even number. So I would need to determine the desired outcomes. Well, there's 1 3, and there are 3 numbers that are even numbers. So that should tell me that I have a 4/6 chance, or about a 66 and 2/3% chance of landing on a 3 or an even number. Again, these are just simple or single probabilities. Let's now look at this in the context of a more complex or compound probabilities. Let's pretend for a moment that I roll a single die. I want to know the probability of landing on 3, and then picking that die up and landing on 3 again. Well, the probability of my first event was 1/6. The probability of my second event was also 1/6. And remember that these are independent events. What I rolled before doesn't impact what I'm going to roll the second time. Once I've done that, I can multiply those probabilities together to find the probability of my total event. In this case, it would be 1/36, or about 2 7/9% chance that I land on a 3 and then a 3. And you can see that probability is really small. Now let's look at rolling 2 dice. And we're going to see what might happen if I roll 2 dice. Well, if I want to know the probability of landing on a 1 and a 1, I would need to determine, well, how many possibilities are there for that to occur for each event? In this case, I have a 1/6 chance that my first dice lands on a 1, and a 1/6 chance that my second dice also lands on a 1. This would tell me that I have the same probability, a 1 in 36 chance, or about 2 7/9% chance that I land on a 1 and a 1 with 2 separate dice. Let's go ahead and talk about probability of pulling something out of a bag. In this case, I've got a bag of marbles, but that's kind of boring, so I'm going to turn these marbles into starburst, because I'm kind of craving some candy right now. So let's pretend like I've got my favorite starburst, which always seem to have the least amount in the bag, which are the pink ones. And maybe those red starbursts, which there's some of those in the bag, and finally, those darn yellow starbursts that always seem to fill that bag up. Well, let's look at probability of some compound events in this example. Let's think about the probability that I were to pull out a strawberry, my pink starburst. Well, looking at this bag, I can see that there are 2 of those pink starbursts out of 10 total starbursts in the bag. That would give me about a 20% chance that I were to pull out a strawberry starburst. But if I wanted to determine compound probability, what's the chance that I was going to pull out a strawberry followed by another strawberry? I want to get really lucky and get my favorite 2 types of candy. Well, in this case, my first event would be a 2/10 probability. However, my second event is dependent. Once I've taken that first strawberry out of the bag, and I've definitely already eaten it, my probability for my second event has changed. My probability for that second event is now 1 strawberry out of 9 total left over. In this case, just like we've done before, we're going to multiply those 2 probabilities together, and I'm going to see that I have about a 2/90th chance of getting 2 strawberries in a row. In this case, that's about a 2 2/9% chance that I get both strawberries in a row. Pretty unlikely. Well, let's look at something that might be more likely to happen. In this case, picking a strawberry followed by picking one of those lemons. Well, the probability of my first event was 2 out of 10. The probability of my second event is still dependent. Although there were still 4 yellow or lemon in my bag, there are now only 9 total. So that means my second probability is 4/9. Again, once I've done that, I can multiply these things together and figure out my new probability. In this case, I have about an 8/90th chance of getting a pink followed by a yellow. In this case, that would tell me that I have about an 8 8/9% chance of pulling out a pink and a yellow starburst, or a strawberry and a lemon starburst. That is how complex probabilities work, and that's also why it's really important to understand independent and dependent events. Let's quickly talk about experimental probability, although we're not going to do an example here. I will let you choose if you do that on your own. Remember, experimental probability is the actual intended outcomes over the total attempts. We've already talked about the theoretical probability of flipping a coin and landing on heads being 1/2 or 50%. Well, if we were going to do experimental probability for this, we know we would need to build a table that have our possibilities, heads and tails, and we need to record data showing what actually happened. So maybe here's an example of what happened when I flipped the coin a few times. In this case, I ended up with 5 times being heads over 12 total possibilities, which was equal to about a 41 2/3% chance. Remember that experimental probability and theoretical probability don't always match up exactly. And we have talked about the more experiments or the more total attempts that you try, the closer to our theoretical probability that you will always get. Now, let's talk about experimental probability with some more compound or complex events. Let's go back to that probability of doing heads and heads with 2 different coins. Well, we've already described that it's a 1/4 chance of happening. We would need to build a table just like we did before. And our table would need to include the possible outcomes that could happen in this case. In this case, I'm flipping 2 coins, so one possibility would be my intended outcome. That would be that I would land on heads and heads. Another possibility, I could possibly land on heads and then tails. Finally, I could land on tails and heads, noticing that that is a different outcome than what I had before. And I could also land on tails and tails. Once I've done that, I can build my table and I can start running my experiment. And I would just need to keep track of my events, what happened, and my total attempts. In this case, one quick thing to make note of is that our table gives us a little bit of a clue of our theoretical probability. In this case, we're going to see that there were 4 possible outcomes, and we see those 4 possible outcomes there, and just one of those possible outcomes were what we were looking for, and we see that possible outcome right here. So again, that's how you would calculate our experimental probability for a problem like this. I hope that gives you a good idea of how we can work with these probabilities. Good luck.